In today's video, we're going to keep working with anti-differentiation, but today we're going to be learning a method that's going to help us anti-differentiate much more complex functions than we've been working with so far. So before we dive into this new method, I want to take a look really quick at a function and go back to derivatives. So here we have our function y equals e to the cosine of x, and we need to find the derivative of the following function. Now, hopefully we recognize right away, when I look at my function, since we have e to the cosine of x, this cosine of x here is going to trigger chain rule when we differentiate. So when we're differentiating using the chain rule, we know that our derivative, dy dx, we're going to take, we know e to something, that derivative is just e to that same thing, so we have e to the cosine of x, but now we need to multiply by the derivative of cosine x, which we know is negative sine x. So I know that my derivative is negative sine of x times e to the cosine of x. So, keeping in mind this chain rule, now we're going to look at functions that we need to anti-differentiate that have come about because of chain rule. And so we need a method to essentially undo that chain rule when we're anti-differentiating. So that's what we're going to be learning today, is what we call substitution, or what we call U substitution. And you'll see where that comes in just a minute. So, our example here is to integrate the function sine of x times e to the cosine of x dx. So we can see here, this function is really closely related to what we did here. We're just missing a negative. So I expect our antiderivative is going to look something like this function here, e to the cosine of x. But we need to figure out how we get back to that point. So here's what we're going to do when we're using U substitution. Now, with U substitution, we will always use this variable u. That's part of our standard notation when we're doing substitution. So the process is to choose a function u. And the idea here is when we're looking at our function, what we want to ask ourselves is what triggered chain rule. And so here's what I mean by that. When I'm looking at this function, I know that if I had e to the x, we'd be fine. There wouldn't be any chain rule there. But as soon as we take e to something other than just x, we're going to need our chain rule there. So I know this cosine x here is what triggered our chain rule. So I'm going to go ahead and I'm going to set u, for this example, equal to the cosine of x. Again, and that's because e to anything other than x is going to cause chain rule when we're differentiating, and so we need to take that into account when we're doing our anti-differentiation. So that's the first part, is finding that function. Second part we're going to do is we're going to calculate du, right? Du is just the derivative of u. So if I'm looking at my function here, I'm going to take du is equal to, the derivative of cosine is going to give me negative sine of x, and we're going to write this like we did with differentials. Instead of du dx, we're going to say du equals negative sine of x times dx. So we're going to write that like our differentials. Now, the next step we need is to solve for dx. So we're going to go back to step 2, and we're going to get dx by itself. We're going to isolate dx. So in this case, if I want to do that, I know I need to multiply both sides by 1 over the negative sine of x. So I know that dx is going to be 1 over negative sine of x times du. So now I've solved for dx. All right. At this point, we have some information here that we're going to need to go back to our original integral with. So here's what we're going to do. We're going to take these pieces and we're going to substitute into our original integral. So here I had the integral. I'm going to keep my sine of x. Now I have e. Instead of cosine x, that's my u here, because we said u was equal to cosine x. So I'm going to highlight here. Cosine x is what became our u. And now dx, we said that dx is 1 over the opposite of sine of x times du. What we're really looking to happen here is for our x's to drop out so that we're left just with an integral that's just in terms of u. So let's see what happens here. If I look at my integral now, I have sine of x over negative sine of x. So those sine of x are going to cancel. And so I notice that I'm left with negative e to the u du. So now I have an integral that's all in terms of u and something that's much, much simpler to anti-differentiate. We know how to do this with the rules we already have. I know that integral is just negative e to the u plus c. Again, this is an indefinite integral, so we need that plus c. So we just did step 4. We took the integral. Now the last thing we're going to do, instead of leaving this u here, we're going to replace that with the function we had up here. So now I know that integral is equal to negative e to the cosine of x plus c. And that is the value of our antiderivative. So obviously there's a lot going on here, a lot that's new, so we're going to go through several problems so we hopefully get the idea and kind of start to learn this process. So let's go ahead and look at number 1 below. And I'm going to move this up. All right, so I'm looking at number 1, and again, I'm trying to decide what's the thing that's going to make chain rule apply. And so if we think back, again, if we were taking just the square root of x, we would be fine. That wouldn't force the chain rule. However, because we have this 5 plus 2x cubed here, that's going to require us to use chain rule. So that's what I'm going to pick for my u. So my u, I'm going to make 5 plus 2x cubed. So that was step 1, choosing function u. My next thing is to calculate du. So I'm just taking the derivative with respect to x. So my first term is a constant. That's going to be 0. My derivative is going to be 6x squared dx. Now for the next step, I want to isolate dx. So I know that dx is going to be 1 over 6x squared times du. So now we're ready to take this information that we have here and substitute it into our integral. So now I have the integral x squared times the square root, and now we're going to substitute for our 5 plus 2x cubed. We said that was u, and dx is 1 over 6x squared times du. And again, we're looking for those x's to drop out. I want an integral ultimately that's just in terms of u. So if I look, I'm noticing that my x squared is going to cancel with this x squared. And so if I pull out my constant, what I have is 1/6 times the integral of the square root of u du. And so again, now I'm back to something that I can easily anti-differentiate. So the square root of u is u to the 1/2. So if I add 1 to 1/2, I'm going to get u to the 3/2. I'm going to divide by 3/2, which is the same thing as multiplying by 2/3. And then I have to remember I have that 1/6 out front. So that's my antiderivative. I'm going to do a little simplification. I have 2 over 18, which is going to give me 1 over 9. And again, instead of that u, we're going to go ahead and plug our function back in. So 5 plus 2x cubed to the 3/2 plus c. And that's going to be the value of our indefinite integral. All right, let's do another one. Okay, the first question I'm going to ask myself is, what would cause chain rule to happen in this situation? Hopefully we all recognize this 2x squared here is what's going to trigger the chain rule. So that's what I'm going to make my u. So u is equal to 2x squared. We're going to differentiate, so du is 4x dx. And now I'm going to solve for dx. So dx equals 1 over 4x times du. So there's all the pieces that I need to go back to my integral now and substitute. So now I'm going to have the integral of x times the cosine 2x squared was what became our u. And dx, we know, became 1 over 4x times du. Again, we're hoping that something's going to cancel here, and by that something I mean our x's, and here they do. This x is going to cancel with this x. I'm going to pull my 1/4 out front. So I have 1/4 times the integral of cosine of u du. Again, now we're back to something much, much easier to antidifferentiate. I know the antiderivative of cosine u is just sine. So I have 1/4 sine of u plus c. And we're going to go back now and plug in our u. So I have 1/4 times the sine of 2x squared plus c. Now, don't forget that you can check these by going back and by differentiating to make sure that you did it right. So I'm just going to check this one out here just to show you. So I know that a constant times my function, the derivative is just going to be the constant times the derivative of my function. So I know the derivative of sine is cosine. My insides are going to stay the same. And then I need to multiply by the derivative of the inside, times 4x. Now, this is a constant term, so when I differentiate, that goes to 0 and drops out. Now, if I simplify it, the 1/4 and the 4 are going to cancel out, and that's just going to leave me with x times the cosine of 2x squared, which is exactly what I had in my integral. So I know that I've done it correctly. So it's certainly worth the time to check it out to make sure that you've done it right. All right, maybe we'll do one more. And then we have one other thing to talk about here. I'm actually going to go ahead to number 4 here. Now again, I'm looking for what would cause chain rule here. I know anytime I take the trig value of something other than just that variable, so in other words, if we're secant theta, we'd be fine, we wouldn't have an issue. But now I have theta plus pi over 2. So I'm going to make that my u. So my next step is to differentiate that. Du. Now, the derivative of theta is just going to be d theta, and my pi over 2, that's just a constant, so that derivative is just going to go to 0. So I actually have everything I need right now. So now we go ahead and substitute. So I have secant theta plus pi over 2 is just our u. Here, tangent, and again, theta plus pi over 2 is our u again. And d theta, we said, is just du. So this one is actually a lot simpler. And I should go back and say, actually, this would not trigger chain rule here, but we can handle it the same way using this u substitution. So now I have my integral all in terms of u. Again, this is easy to anti-differentiate. The antiderivative of secant u tangent u is just secant of u plus c. I'm going to go back and substitute theta plus pi over 2 for my c, or for my u, excuse me, and now I have my antiderivative. Okay, so now I want to talk briefly. So far we've looked at integrals that were indefinite integrals. So in other words, there was no upper or lower limit of integration. So we used our plus c. But we can also use this property, or excuse me, this rule, substitution, when we have definite integrals. There's just a couple things we have to keep in mind. So here it says when we use substitution with a definite integral, we can avoid resubstitution by changing the limits of integration. And so here's what we mean. We start off the same way we have been. So I'm going to look for what would trigger chain rule. And here I notice this inside the squared certainly would cause chain rule to happen. So my u is going to be 2x squared plus 1. I'm going to take the derivative, and my derivative is du equals 4x dx. And so to isolate dx, I have 1 over 4x times du. So I have the pieces that I need now to go ahead and substitute into my integral. So now I have the integral, and I'm going to leave the bounds off for right now. I'm just going to focus on rewriting this integral. So what I have is 4x over, here's my u, that u is being squared. So 4x over u squared, and then dx is times 1 over 4x du. So I'm happy to see here that my x's drop out. So what I'm left with is just 1 over u squared du. Now, these limits apply to the function in terms of x. So if I'm going to integrate with respect to u, I need to change those limits. So here's what I do. I take my function u, and I evaluate it at these two values. So I'm going to find u of 2. I'm just going to take 2 and substitute it into u. So I'm going to have 2 times 2 squared plus 1. That's going to give me 9. And I'm going to take u of negative 1, which is going to give me 2 times a negative 1 squared plus 1, which is going to give me a 3. And now I'm going to use those new limits for my integral. That just prevents me from having to go back and resubstitute for x. I can just leave everything in terms of u. So now I'm going to anti-differentiate like normal. I know this is the same thing as saying 3 to 9 integral of negative u to the negative 2 du. So I'm going to add 1, and I'm going to divide by negative 1. So negative u to the negative 1 from 3 to 9. Again, that's the same as negative 1 over u from 3 to 9. So if I evaluate, I have negative 1/9 minus a negative 1/3, or negative 1/9 plus, I'm going to rewrite this as 3/9, and the value of my integral is 2/9. Oh my goodness, I'm sorry, I went off the page there. There you go. So again, changing these limits here just allows me to not have to go back and re-substitute. But I have to make sure if I'm going to integrate with respect to u that I'm evaluating at those limits that have been changed. Okay, we'll leave it at there for today. I think we'll do a few quick together tomorrow as a warm-up, and then obviously you'll have lots of time to practice with this because there is a lot of stuff going on here. See you tomorrow.